Okay, so let's continue on the architecture of the discharge. So, so last week you have already learned that in a DC discharge tube, from cathode to the anode, there are several zones. So if we just look at the brightness of plasma, right, between cathode and anode, there will be a very thin layer named cathode layer, and then a bright negative glow, and then a continuous positive column. And at the right end, there is a thin layer of anode glow. So usually in a DC discharge system, these regions will emit light, or we can say these parts are luminous. And the other regions between this luminous zone, these other regions are dark space. So the architecture of the discharge, contains these dark spaces and luminous parts. And based on the analysis, we can measure the luminous intensity distribution, and we can also measure the potential distribution across the discharge tube. So the potential distribution in a DC plasma system is very important, because if we apply a negative bias, right, negative bias on cathode, and the anode is grounded. So before we generate plasma, the potential distribution should be linear, right? Before we generate a plasma, the potential distribution should look like this way. Should be linear. So that the electrical field is constant, right, across this distance before we generate plasma. Okay, so if the gas is an insulating state, the potential distribution should look like this way, linear. But once we generate plasma, the plasma will automatically form several zones, right? And then we can find out the most potential drop fall in the cathode region, okay? And the potential drop in the cathode region is labeled as V sub C. Right? V is potential and C is cathode. And the length of cathode zone, right, is labeled D sub C. Okay, so the potential drop just fall in a very short length region, fall in this region. So if we divided V sub C by D sub C, we can get electrical field near cathode, right, in the cathode zone. So that the electrical field in the cathode zone is very large. But inside the positive column, the potential is almost uniform. So that if we divide the delta V by the distance or by the length of the positive column, we can also get the electrical field. But the electrical field inside the positive column is almost equal to zero, even though there is a very small electrical field. But compared to the cathode zone, the electrical field in positive column is very small. So there are two regions with different characteristics of the plasma parameters. Okay, two different zones. And last week, I have already gone through the reaction in the cathode zone. Reaction in the cathode zone. So at so in this region, on the surface of cathode, at the beginning, ions, cations, bombard the cathode surface, and the cathode surface will emit electron after the bombardment. So at the beginning, the electrons coming out from cathode surface accumulate near the cathode surface, right? And since here exists a strong potential field, electrical field, so that the electrons will start moving, right, toward the negative growth, right, along this direction. And when electrons travels from surface of cathode for a short distance, electrons gain a small amount of energy. And when these electrons meet cations, they recombine together. Recombination. Recombination causes the luminous in the cathode layer, in this cathode layer, luminous. So it is caused by the recombination between electrons and the ions. The ions come from the plasma volume, and the electrons will emit out from cathode surface. Okay, so this part, luminous part, is originated from recombination of electrons and cations. And then the electrons keep moving. No, some electrons keep moving along this direction, and the electrons, when they travel across this region, they can still experience a strong electrical field across this region. So the electron get energies from electrical field, get energy when they travel across the cathode layer, across this layer, D sub C. So when the electrons come to the edge of the negative glow, the electron has very high energy. So these electrons can behave like a primary electron. So when primary electron meet neutral gas atom, they can undergo electron impact excitation. So in the negative glow region, in this region, the major reaction is electron impact ionization. And those electrons are with high energy primary electron, because the electrons got energy by the electrical field across the cathode layer. Okay. And once the atoms are ionized, right? They are cations and electrons, electron and cation pairs, or electron and ion pairs. So this part contributes to the generation of plasma and the sustaining of plasma. So the negative glow is very important in a DC glow discharge. Okay, and once the plasma is generated, there are many kind of species, including radicals. Radicals, right? So if an electron collide with a neutral atom, it might also undergo excitation process. Excitation. So the excitation process will bring the atoms from ground state to an excited state. Excited state. So you should already know that these reactions so these reactions exist in the negative glow. Negative glow, okay. So the gas atoms is ionized to cation, or the gas atoms is excited from ground state to an excited state. Excited state, okay. And later on, the reverse reaction happens, so that the an excited state can return back to ground state. So this is excited state. Return back to ground state. But the energy of the excited state is higher than the energy of ground state. So the energy difference will be released by emitting photons. And usually these photons can fall in a range of UV and visible light. Okay, and some may be infrared. Okay, so this is called the excitation or relaxation. Relaxation or excitation will give the release of photons. And for the other one, when the reaction, when electrons meet the cation, they might recombine together and emit photons again. Okay, so this is recombination. Recombination, and usually the energy of the ion, right, is much higher than the energy of the neutral atom. So the recombination will emit UV light. Okay. So the glow we seen, we have already seen in the plasma system. Came from majorly from relaxation process. Because we cannot see the UV light, we can only see the visible light. But if you use an optical spectrometer, you can record the UV light and the visible light and IR, infrared. So that you can get a plasma spectrum and analyze the metastable states. Okay. So this part is the negative glow. When the primary electron, right? Primary electron collide with primary electron collide with the neutral atom and then ionize the neutral atom. Or when primary electron collided with neutral atoms at ground state, they can excite the neutral atoms to a higher excited state, and then they return back by relaxation, or this part by recombination, and give emit light out in the negative glow region. Okay, and after the electrons, collide with atoms, with gas atoms, they lost a lot of energy. Right? In this region, electron gain energy from electrical field and become primary electron. But after the collisional process, the primary electron lost energy. Okay, so the energy of the electron is smaller than the ionization energy of gas atoms. So when they travel across this region, those electrons cannot ionize gas atom. So it forms another dark space, which is called Faraday dark space. So in the Faraday dark space, there's almost no collisional process. Right? And in the Castle dark space, there's also no collisional process. So collisional process happens in the glow region. And this part is the negative glow. And then the positive column. Okay. So after the electron travel for distance or travel across the Faraday dark space, they become thermalized. So even though we said that there's almost no electrical field in this region, but actually there are mild electrical field, so that the electron can gain energy, a small amount of energy, and become thermalized plasma. Thermalized plasma, so that the electron temperature follows the Maxwellian distribution function. Maxwellian distribution function. So in this region, actually in this region, the electrons become thermalized, and their energy distribution function look like this way. So that there are small amount of high energy electron in the high energy tail region. So this high energy, the electrons in this high energy tail region contribute to the ionization and the excitation in positive column. Okay. But in the negative glow, the ionization coming from the collision of primary electron with gas atoms. But in positive column, right, most electrons have energy much smaller than ionization energy of gas atom. But small amount of electrons can have energy higher than ionization of the gas. And this part of electrons contribute to the glow or the ionization process inside the positive column. Okay. So this slide explain the phenomena in the cathode zone region. In the cathode zone region, from the cathode surface to the edge of negative glow, right? And the physical processes in the cathode zones. And there are several important factors or parameters we need to know. If you design a plasma system, you have to choose cathode material, the cathode material, okay? And cathode material, the cathode can contribute to the electron emission by ion bombardment or by the photo irradiation. And this parameter is the gamma factor, right? So if you go back to the previous slide, you can see the gamma factor is one of the tungsten coefficient. There are two tungsten coefficients. One is the gamma factor. It's a gamma factor, the secondary electron yield, okay, from the cathode surface or from the chamber wall surface, okay. And the other factor for tungsten coefficient, is a combination of the ionization energy of gas and electrical field inside the system. The other factor, alpha, or var epsilon factor. So in a normal glow discharge, so I think you have already known there are different kind of glow discharge. Normal glow discharge in this region. So in this region, when we increase the current, the voltage across the cathode and the anode doesn't change much. So this part is the normal glow discharge. So in a normal glow discharge system, okay, we can see the cathode fall, normal cathode fall, the values of normal cathode fall. So in this row, the table shows different cases. And in this column, the column shows the materials for the cathode. Materials for the cathode. So if you pick up a cathode material, for example, if you use silver as the cathode material, and then you can check out the cathode fall for different gases. So right here, helium, for example, helium. For the helium plasma, it requires a cathode fall of 162 volts. And for neon, it requires 150 volts. And for argon, 130. Right? And we have already known helium, neon, and argon belongs to the inert gas. And the ionization energy, the sequence of the ionization energy is that helium greater than neon and then greater than argon. Right? So compared to helium, argon can be ionized easily. So that the cathode fall is smaller than the cathode fall in the helium plasma. Okay. And nitrogen and oxygen are difficult to be ionized, right, compared to the inert gas. So if you use pure nitrogen, you want to generate plasma, No, it's not very easy, pure nitrogen plasma. So sometimes people will mix inert gas and with working gas. One is carrier gas, the other one is working gas. So for example, you can mix the argon and nitrogen, or argon and oxygen, to generate a mixture of plasma. A mixture of plasma, okay. And okay, this part is the K4. And also, if you use alkali metal, alkali metal like potassium and sodium, potassium and sodium as the cathode material, you can get plasma easily because the gamma factor is larger. For cation, for alkali metals, they are easy to be ionized, right? To positive charge or to cation. So it means they can release electrons easily. So the gamma factor for the alkali metals is large. Okay. And table A.2 shows the cathode layer thickness for the normal glow discharge. So the unit for the cathode layer thickness is centimeter tall, right? So actually it's P times D. P is the pressure of your plasma system. D is the cathode layer thickness. Okay. And from this table, we can see for most the systems, the cathode layer thickness is a little bit smaller than 1. A little bit smaller than 1 centimeter tall. Okay. And this value is related to the patching curve. To the patching curve here, right? And the horizontal axis has a unit of centimeter tall, because this value is given by P times D, pressure times distance. Okay, this is a cathode layer. So actually, the cathode layer thickness, for example, for the hydrogen plasma, you can see the minimum, the PD value for minimum breakdown voltage is around 0.8 or 0.9 centimeter tall, right? Less than 1. And for other gases, for example, for air, the value is around 0.4 here, small, right? A little bit smaller than 1 centimeter tall. Okay. Right. So for the most the systems, so for example, if you generate hydrogen plasma, and you use different cathode material, and then the cathode layer thickness PD fall in this region, a little bit smaller than 1 centimeter tall, and here are other systems. So the cathode layer thickness is the P times D, and D is the DC. The cathode layer is here, cathode layer, okay. So if we have a system with the normal cathode layer thickness equals 1 centimeter tall, 1 centimeter tall. So if you generate a plasma at a pressure of 0.1 torr, okay. So this is usually the pressure we we can use to generate the plasma for PECVD. PECVD is between 0.1 and somehow a value smaller than 1 torr. Right? So if you have a pressure of 0.1 torr, and if you generate a DC plasma, you can see the cathode layer thickness should be around 10 centimeter. 10 centimeter cathode layer thickness. Right. So if you have a plasma of a pressure of 0.2 torr, the cathode layer thickness will shrink to 5 centimeter. 5 centimeter. So actually, the the length of the cathode layer depends on the pressure. So if you keep decreasing the pressure to 0.01 torr, 0.01 torr, the cathode layer thickness will expand to 100 centimeter. You need a system with a length of 1 meter to generate a stable DC plasma. If you operate the system at a pressure of 0.01 torr, which is 10 millitorr, 10 millitorr, 10 millitorr. Okay. So if you design a system, you must be aware of this part. Okay. So later on in the chapter of the DC glow discharge, we can see this again. And actually, in industry, the system doesn't need to have a very big size. Okay. So if you use RF radio frequency, the power supply to generate plasma, and this relation doesn't follow. Okay, so if you use RF power supply to generate plasma, usually the cathode layer thickness is around 1 centimeter only. 1 centimeter only. So it's different from DC discharge. But if you generate plasma by DC power supply, you must be aware of the limit of the PD, P times D, okay, this part, okay. And last week, you have already known, in order to generate plasma, there must be a cathode and anode, and the cathode layer and negative glow. Small portion of negative glow. So positive current is not required. It is not required in your system, in your plasma system, right? So especially when you operate a system at low pressure, the cathode layer thickness might be a few tenths of centimeter, and then this part will disappear. Positive current will disappear. But the plasma can exist, and you can still get a stable plasma. And this part is the description of the properties and the reactions and the negative glow. So you have already known that there are excitation, right? Excitation process and ionization process. And this process will subsequently induce the recombination or relaxation process. And this recombination and relaxation process give photons, and it causes the luminance of the negative glow. And the electrons travel across the negative glow, lost their energy by collisional process, right? So and then they can enter the Faraday dark space. And in the Faraday dark space, those electrons are with low energy. With low energy. Okay. And in the Faraday dark space, it is absence of emission. There's no photon emission because there's no recombination and relaxation process. Okay. And since the electrical field in the Faraday dark space is very small, so electrons cannot gain energy when they travel across the Faraday dark space. In the positive column, right, it is a quasi-neutral state. Density of electrons is approximately equal to the density of ion. So it is also called quasi-neutral. And this is the classical definition of plasma. N sub E equal to N sub I. Electron density and ion density are equal, or the charge, positive charge and negative charge, the density are equal. So they are close to the neutral state. But if you confine the plasma in a limited space, you will find out some electron will lose because electron can travel at a faster speed than cation. So the plasma is little bit positive. So the cation or the positive charge density is little bit higher than electron density. So it's little bit positive. So and so that this region is named positive column. And the potential, usually the potential of plasma is little bit higher than the ground potential. Okay. And in the physics of the positive column, here is important. The energy of electrons is around 1 to 2 electron volt. And with the distribution of the electron energy similar to the Maxwellian-Boltzmann distribution. So there are some energetic electrons at high energy tail, and this part of electron causes ionization. Okay, and there are still the electron impact ionization process caused by this high energy tailed electron. So this equation, this reaction still exists inside the positive column, and the collisional process will generate electron and ion pair, and this electron is named secondary electron. Secondary electrons, okay, are generated. Okay, and after this process, the electron keeps traveling across the positive column, and at the end reach the surface of anode. And here is the anode region. Usually, near the anode, there's a region with a positive space charge. So in the anode sheath, usually it is positive space charge. If you have an equal size of the cathode and the anode should have positive space charge, okay, in normal condition. And the function of anode is to collect electrons. Right? So electrons emit out from cathode and travel across your system, and at the end reach surface of anode, and complete an electrical circuit. Okay, so the anode can collect electrons. Okay, and okay, and when electrons and actually electrons and ions collide with anode. Maybe we should jump to this page. Discharge. Okay, this is in the next chapter. So here is the anode. So actually, ions and electrons, both ions and electrons from the positive column will collide with anode. Okay. So this collision will generate secondary electron from anode. So actually, anode also generates secondary electron. And since there's a small positive space charge, these electrons will be pulled out. Pulled out from the anode surface. And when they meet the incoming ions, incoming cation ions, they can also recombine and give the emission. Right. Recombine and give emission, so that the anode the anode surface also shows a glow region, the anode glow. So again, it is caused by the recombination of electrons and the cation. Okay, a thin anode glow region. Okay, so we finished the nature of plasma, the first part of our course. So, do you have any question about the architecture of the plasma, or architecture of the discharge, or the characteristic? Right. IV characteristic of glow discharge, or the patching curve, and the analysis of the Thomson criterion for self-sustaining discharge. Okay, so all these parts are important in this chapter. Okay, the new chapter is a DC discharge. So in our course, I will go through 3 kinds of discharge techniques. So the first one is DC discharge, and then RF radio frequency discharge. So the radio frequency discharge is the AC discharge, but with high frequency AC, and then the microwave discharge. So in previous chapter, we focus on the generation of plasma, the generation process. Okay, and the first slide in this chapter focus on the loss of charge in a plasma system. So there are several loss processes. So if you generate a plasma right inside a system, here the left side is the cathode surface, right side is anode surface, and you might use a stainless steel chamber or glass chamber to confine the plasma or confine the gases inside your system, inside the system. Okay, so once the plasma is generated, there are cations and electrons. So cations and electrons are the charged species, and in order to maintain a plasma, we need a density, a relative, a medium or high density of electrons and ions. You need a certain density of ions and electrons to keep a stable plasma. Otherwise the plasma will fall into a region of non-self-sustaining plasma, or the plasma will extinguish fast. So once you generate the plasma, you need to know whether you can keep the density of electrons and cations at a certain value. But from this figure, we can see the cation and electrons might lose their charges by collisional process. So cations and electrons, when they come to the surface of cathode and anode, right, they might lose. So for example, from the left side, when the cation collide with cathode, they will lose their positive charge to cathode. And on the anode surface, both cation and the electrons come to the anode surface. And some of the negative charge will collected by the anode. And some charges will recombine. Some electrons will recombine with ions. So again, we lost the charge to electron. And when electrons and ions collide with the chamber wall, they also lost their charges. And inside the plasma, when electrons and ions can meet, they might recombine and lose electrons at positive charge and negative charge. So there are several loss process for the charge species. Okay, and we also need to concern the loss of energy by emitting light and by the heat transfer from plasma to chamber wall. So tomorrow we will continue on this part, how to the reason for the maintaining the discharge. Okay, because we need to supply electrons and ions in a system to compensate the loss of the charges.